Okay, good evening, everyone. Welcome to the Sunoikisis Digital Classics Spring 2019 session number 8, which is Introduction to Programming Through R. And our presenters today are Christopher Ohge and Gabriel Bodard, both from London. And this session is first part of 2 sessions. So after 2 weeks, we have a second session using R. So this is to introduce, and in the meanwhile, you can learn yourself more. And then in 2 weeks' time, we will know what to do with it. So without further ado, I will hand this to Christopher.
Hi. Thanks very much for having me. I just wanted to start by reading off the outline of what we're going to cover in this session. I should say that we're covering an awful lot, and we don't expect that you'll fully understand every bit of it. But the hope is that after seeing this introduction, you'll want to learn more about R, and you might have a better understanding about how programming languages work in general. So we're going to start out by generally talking about programming languages that are used in digital humanities and why we're interested in R today, why it's important for certain kinds of tasks. And then after a few minutes of that, Gabby is going to talk about regular expressions, and we'll finish off the session with a somewhat lengthy demonstration of how R works and the tidy text package in R, which I think is a very good introductory package for figuring out how R works. So with that, I will hand it off to Gabby, and I'll be back in a second.
Cool, thanks, Christopher. So yes, I'm really only going to talk for a couple of minutes about a couple of the most common programming languages you're likely to come across if you work in digital humanities, or if you work with people who are have a digital humanities background. These are not the only programming languages in the world, of course, but the most common ones you're likely to come across. And so just a couple of words about each of these. So XSLT, the extensible style sheet language for transformation, is a language which is both written in and is designed for processing XML. So this language would be used if your input data is XML, and in particular if your output is also XML. Then XSLT is really powerful for processing XML in that way. It's most commonly used for taking XML files and turning them into web pages, but all sorts of other things such as indexing and so forth can also be done in that. It's not a particularly powerful language for anything other than XML. It can be used for other things, but XML is really its forte, and that's really the only thing it would claim to be really the best language for. I mentioned that first, partly to get it out of the way, and partly because that's the only language that I can claim to be an expert in. So that would be my favorite programming language, as it were. So the second I'm going to mention is Python. Python is probably the favorite programming language of digital humanities. I toyed with the idea of putting in parentheses after Python does everything, because that's what Python heads claim. It is most often used for text and data processing of various kinds, but it does have many libraries for all sorts of different kinds of functions, including XML processing, including mathematics, including visualization, 3D modeling, image processing, all sorts of things as well. It's very versatile, and it's very popular. Some Python heads would claim that it is the best programming language you could possibly use. I won't claim that, but it is one of the most popular programming languages in digital humanities. So it's a fairly good idea to understand a bit about what it is for that reason. The next language I'm going to mention is JavaScript, not to be confused with Java, which it has no real relationship to. This is a language which is very often used for client-side programming in web pages. So things like web pages where you can resort a list on the page by clicking on the head of that list, things like that, things that happen in your web client. Those have often been programmed in JavaScript, and so it's very much used in web design. In that it's very powerful for that reason. It's not very often, not never, but it's not very often used for more general programming outside of that context. In contrast, PHP, again, it's a fairly general programming language that can be used for lots of things, but in digital humanities, you'll most often see it used for rendering structured data, very often database data, as web pages. And unlike JavaScript, PHP does its work on the server side rather than in your client, most often as deployed. So you will very often not necessarily interact directly with the PHP, but PHP will be what's behind your website, and it's turning your data into various web constructs. And the fifth example is this language called R, which probably Chris will claim can do all of the above, but is particularly commonly used when people need to use the things related to statistics and visualization of data. So Chris will then tell us a little bit more now about why R is particularly appropriate for what we're doing today.
Yeah, and I think that brings up an interesting point that I want to emphasize, which is I have learned a bit of Python, I've learned a little bit of JavaScript, and I learned those before I learned R, and when I learned R, I just happened to like it a little more. Sometimes your facility with a programming language comes down to personal preference. Sometimes you might need to learn a new language because the language is more suitable to the kinds of output and material that you're interested in. But for some reasons which I can't fully understand myself, R just worked better for me, and I was lucky that I was working on text processing and data mining and visualizing data. And so that was a lucky break in my part. But there is no language that's really better than another, despite what some people who program in Python might say. We can leave those arguments to the engineers who probably know much more about that than any of us here. So as Gabby said, if you're interested in working a lot with XML, you should probably just quit this session right now and go figure out how to program an XSLT. But that said, there are XML libraries in R that work for processing XML. So that just shows you that there's a lot of flexibility in these programming languages, and you can kind of self-educate based on what you're seeing here and what you see elsewhere on digital humanities resources to find out what might work for you. Now, R, in my mind, has some really distinct advantages. I think most people who use R would agree that their visualization libraries are probably the best, or at least the graphics modules that they have work really well, and they're really intelligent. The defaults are excellent. And secondly, with R Studio, which we'll play around with more shortly, it's really easy to report your results. You can report your results not only within R Studio, but you can also publish them as R Markdown files into web-ready HTML files that show all of the results of your code, as well as showing your code in a friendly HTML format. It's also a very functional language, and this just means that almost everything you do is accomplished through functions. And for some, that means more readable code, although that's a relative concept, because I don't think that Python is that readable to me, and yet a lot of people who program in Python think that it's extremely readable and R is incomprehensible. So again, there's a bit of subjectiveness that we need to consider when we're thinking about programming languages. And also, kind of following on from what Gabby said already, R is a language that was built primarily by data scientists and linguists. So it's really optimal for statistical analyses and text and data mining and visualizations. You might want to use Python if you're interested in more general purpose programming tasks, and particularly for natural language processing tasks. The NLTK package in Python is excellent, and there is one in R too, but Python is sort of ahead of the game, I think, on that front. R also tends to be used by academics and researchers, so it works pretty well with research questions, particularly those of us who are interested in statistical methods on literary texts. It has a very strong user community, so CRAN, which is the open source repository for R, has 120 or 12,000 packages that are currently available and maintained. I would be remiss if I didn't mention a couple of disadvantages. And to me, these have not been significant disadvantages, but for some kinds of projects, they might well be. And one is that it's fairly slow with large data sets. But if you're dealing with large data sets and you really want to learn more about handling bigger data sets, you can download RStudio's server application, which I think would help a lot in that case. It's also kind of a non-standard programming paradigm, according to what I've read about R. And it's also based on a commercial language called S and S+, and this was developed in the 1990s by AT&T and Bell Labs. So it was kind of a language that came out of a commercial product and is slightly different from the way you read some other languages. And before I hand it back to Gabby, I just want to muse for a second about why there are so many programming languages. This was something I didn't know until recently, which is the basic fact that the central processing unit of the computer doesn't understand any programming languages in themselves because the CPU takes in machine code. And this is what runs directly on the computer's hardware. And machine code, of course, is just a series of tiny numerical operations, which is basically unreadable to a lot of people. And so what programming languages do for us is to translate the machine code. And they're interpreted as opposed to compiled languages in the sense that they bridge the gap between machine code and computer hardware and the human programmer. So when we're talking about our source code, when we're writing in R, for example, we're really talking about a set of statements in a preferred language that interacts with the machine code on the hardware. And source code is written just as plain text in a text editor. In the notebook, you'll notice that I say do not use a word processor. There are plenty of good reasons to not use a word processor, but particularly when you're writing in a programming language, you must not use a processor because word processors themselves have code under the hood that get in the way of all kinds of things. And finally, the computer knows source code by the file extension. So when you go into a plain text editor and you want to write R code, all you have to do is save that plain text file with the .r extension, and the computer will know that that's an R script. With JavaScript, you would label it .js. And with Python, it's .py. So the computer knows how to translate that extension between the plain text and the hardware. We're going to be using today what's called an IDE, which is an integrated development environment, to help us understand R code. A lot of people use IDEs. If you don't know about them, I'm sure you've heard of programs like Oxygen for editing XML, and Spider, and PyCharm, and Anaconda for doing various things, including Python writing. In my mind, the only IDE that's worth using for R is RStudio, and if you go to the wiki, you'll find installation instructions if you already haven't found those for downloading that IDE. Now, having said all that, before we get into some of the details of R, I'm going to hand it back to Gabby, and he's going to show us how regular expressions work.
Great, thanks, thanks, Christopher. So yeah, the reason we'll start with regular expressions is partly because they're very much to do with recognizing and processing individual strings of text, which is one of the most common things we're going to want to do when processing text, and also because regular expressions are a sort of independent language of their own, which work within whatever programming language you're using. So what I'm talking about for the next 10 minutes or so is exactly the same as you would be implementing if you were using regular expressions in R, in Python, in XSLT, in any other programming language, or in most text editors. If you search and replace and you say turn on regular expressions, you'll be using exactly the same syntax that I'm talking about now. The interface that I'm using is one of many interfaces that are available just for playing with regular expressions online. There's regex 101, regex tester, various other different things on there that you could play with. I've just chosen regex tester, which is one of the ones which is linked from the bottom of the session page. And I've also put next to that a link to this this regex cheat sheet, which has various information about regex and regex syntax in there for you to play with, and we'll come back to that in a moment. If you open regex tester as following that link, you can also, by selecting on the right here, you can get a small mini cheat sheet of regex that gives you a quick overview of some of the most common commands that you may need for that. But I'm just going to demonstrate, just by way of example, a few of the things that you can do with regular expressions. So a few of the ways you can use that to find strings of text. I'm just going to paste in a text string more or less at random here in the text part of this window. I hope that's big enough to see. I wonder if I make it a little bit smaller, will it still be big enough to see? Yeah, I think that's still okay, isn't it? I just want to be able to see what's going on in there. In a regular expression window, you basically you can search for any string of characters, and the simplest way to search for a string of characters is just type in the string of characters you're interested in. So if I'm interested in the letter A, I put in an A up in that bar, and it highlights every single A in this text. That's what will be found by the script that uses this regular expression to find that character. If I then search for AR, it'll find only A when followed by an R, okay, in various places in here. So far, so straightforward. There are then what are sometimes called wildcards, or classes of characters that can be found, and the most common one of those is the dot. So if you type a dot character, it doesn't find you a full stop. It finds you every character that appears in the text. Every character except for a character return, I guess. So any character in your text is now highlighted by that string. So if I said I wanted to find A.R, that finds me an A followed by any character followed by an R. In both of the cases, the character in between was another R, but it needn't be. If I used a different character, I did A.B, it would find barbarians, which also has an R in between. No examples, 2 A's, no. A.E finds every string A, anything E. So there you can see several examples with a different character in between. So the dot is the simplest thing in there. So just going to the cheat sheet for a second, this is what you find under more characters. And I think this is the most useful place to start here. So the dot finds you any character. If you want to find just a full stop, then you need to use this escape character, the backwards slash character, followed by the dot, and that finds you just literal full stops, periods in your text. Okay, and there's various other characters that have special meanings that you need to have an escape character to be able to find them. So one of the other useful things that you can use in regular expressions are these quantifiers, this green block in the cheat sheet. This is where you can repeat the pattern that you've just searched for, and you can find it multiple times. So if I look for any character, you can just about see that it's finding each character in there, but singly. If I say I want to find any character 5 times, it finds every string of 5 characters in there. You can see the little white marks in there are each different block of what has been found. One thing to notice here is that technically, the string of 5 characters from 1 to that 0 there is 1. There is also a string of 5 characters from the full stop to that space. See that, what's something? That is not being found because the regular expression doesn't start until the previous set of search results has ended. So if you want to find overlapping sets of search results, you have to do different things to find them. And again, the most common thing if you want to find any number of characters is to use this asterisk character, which means 0 or more instances of any character, and that finds, of whatever the previous pattern was, which in this case is any character, and that finds then the entire line of text. Note that this is one line of text in a computer file. The word wrapping on the page, on the screen, is just to make it easier to read. The other thing that is going to be useful is to be able to give optional sets of characters. So by which I mean classes of characters. So if I say I want to find any vowel, I put in square brackets, and it finds any one instance of a vowel, and it's finding all these various instances in there. So it's not finding the whole string, A, E, I, O, U, it's finding any one character out of that string. So I could say, find me any M followed by a vowel, right, or something like that. And that would only find me the one vowel, it wouldn't find me multiple vowels. I could then say, find me any series of vowels, one or more set of vowels, which for some reason it's not finding with a star, but okay. You maybe can't see much difference when I say plus in there, but that's finding one or more vowel. The difference between that and just finding a vowel is you see those 2 vowels together under Phoenicians, in the middle of Phoenicians there, are 2 sets of search results when we don't group them, and when I say plus, it finds that as a single search result because it's found 2 vowels together. So it's not 2 separate search results, it's just one. So those are the main building blocks of a regular expression. These then allow us to combine them in various ways and do various kinds of searches for various patterns in there. The other thing I haven't mentioned is the 3 special character classes that are going to be most useful are \W, which finds you any alphanumeric character. So you notice here it's finding all the letters and numbers, but not the spaces and not the punctuation characters and parentheses and so forth. \D, which is any digit, so it's finding the 0s and 1s and 2s and so forth in this page. And \S, which finds any white space, and that's spaces, tabs, and new line characters are being found by the \S command. If you put the letter in any of those 3 patterns into uppercase, it finds the inverse. So \W finds you any non-alphanumeric character. So that's all punctuation and spaces and so forth. If you say \D, it finds you all non-numerical characters, and if you do \S, it finds you all non-space characters. Okay, so you can then combine these in various ways. Let's say I wanted to find any word here that ends in a vowel followed by S. So I know how to find any vowel, A, E, I, O, U in square brackets. So that finds me all the vowels. I can then say any vowel followed by an S. And so how do I know if it's at the end of the word? Well, it's followed by a space. Okay, so there's vowel S space. That finds me lots of words ending in S. Ending in vowel S. It's missed Argos over here, it's missed Halicarnassus over here, because those words are not immediately followed by a space, they're followed by punctuation. So let's say instead of putting a space in my expression, I put in \W, that finds me any non-alphanumeric character, and that finds me all the cases where vowel S is followed by either a space or a punctuation character. Okay, let's say I want to find all words that begin with T and end with S. So I can say T, any other character, 0 or more times, followed by S. Well, that's found a longer string than I expected, because this isn't finding me any word beginning with T and ending in S. This is finding me any string beginning with T and ending in S. This is also missing the word this at the beginning of the sentence. So the first thing we can do is we can have an option there to say I want to find both uppercase and lowercase t, but that's made it even worse. That just finds an entire string starting from there. So I don't want to say just any such string. I want to say any string where the content is not any number of any characters, but any number of non-space characters, let's say. So now we're only finding any string, continuous string of characters beginning with T and ending in S. Still not quite what I was looking for, because only 2 of these 5 search results are full words. So I need to say, firstly, that my string has to end with with a non-character string, and it also has to begin with a non-character string. I mean, there's other ways, there's better ways to define word breaks in regular expression, but this is just an example of building up a query with lots and lots of. So there's only 2 words in here that actually begin with T and end in S, and we've done this by combining various different strings. It might have been better, rather than saying non-space, to say alphanumeric character in there with a /w, because you might get a word, 2 words that have punctuation in the middle and no space, such as an M dash, that you wouldn't want to find as if a single thing. This, however, wouldn't find, as Ellie is pointing out in the chat, this wouldn't find words that do contain punctuation, such as abbreviated words in English don't or can't, or words in the genitive ending apostrophe s. So my \S would have worked better for that than they would have here. In fact, rather than these various hacky workarounds, the simplest solution to this is to go back to the original **, finding any character in there, but to use this command under more quantifiers a bit further down, which points out that the asterisk character, saying 0 or more instances of the previous test, this is a greedy quantifier. This means it will find as much as it can in there. That's why it's finding almost the entire line rather than just the individual word. But if I add a question mark after that asterisk, then it is being non-greedy, and this will find the shortest possible string that it can find of that kind. In this case, that hasn't done quite what I expected, because it is still finding, in some cases, the shortest possible string is more than 1 word. So that hasn't solved this particular problem, but it does illustrate one way of finding shorter results in this instance. And yes, no, that is seeing everything I'm expecting. So I might still end up saying actually just use \S as my thing, and then the question mark doesn't make any difference anymore. I think the best way to learn about this any further is just to play with this. Look at the cheat sheet, which will have many more examples of things that I haven't talked about. I didn't talk much about the quantifiers where you can say exactly how many times you want a character to appear. This is something you will try out. Put maybe a slightly larger piece of text in there. I just copied the first couple of paragraphs of Herodotus' histories in translation in there, because that had these square brackets and numbers and things in there which were quite nice for playing with. But I would just experiment with and play with it. Remember that if you try to search for a square bracket, that expects that to be part of a pattern. So you instead search for / square bracket, that finds literal square brackets in the text. So I think I will leave that there. And hand back to Christopher. One of the things we'll see over the course of today, or over the course of the exercise after, is that many R scripts will have regular expressions embedded in them in various places and in various ways. So back to Christopher.
Thanks. What I'm going to do now is share my screen with you to show you the R work. Can everyone see this? Yeah.
Yes, it's fine.
Good. Okay. So what we're looking at here is the RStudio interface. So hopefully you've all downloaded R and then downloaded RStudio, and we have instructions for that on the wiki. What you will do is once you download the notebook file that's also on the wiki, you'll get this file, which is previewed here, and we're now in the section about R Markdown. So what we're looking at is an R Markdown file, and for those of you who don't know Markdown, it's basically a simplified markup system based on HTML that renders text into web-ready display. It's basically a way of writing shorthand for HTML. This comes in handy with R because what we're doing here is we're not only writing R code, but we're also publishing the results of the R code in an HTML file through R Markdown. So what I want to do before I get into some of the code and some examples of regular expressions is just to show you what kind of syntax R employs, from the very basic to the not so basic. And one of the reasons why we use R is because it's very good at doing math. As Gabby said earlier, it's very good at doing statistics. It was built by statisticians and linguists who were interested in statistical methods. So naturally, there's a lot of mathematical operations built in. And that makes things very easy for those of us who want to do things like tabulate word frequency ratios or type token ratios or things like that. But you can also use R in very simplified ways, as I'm about to show you quickly. Even if you're making a travel budget for your next holiday and you want to find out what might be a better choice given various options, you can use an R script to do some comparative work for you. By doing this, I'm going to highlight this code block here, which is prefaced by the curly bracket R and curly bracket. This is done by simply clicking up here and clicking on insert and then R, and it adds this R script. And all I've got here is the price of a calculation of a trip to Seattle. And if I click Command Enter within the code block, you get the result here, but you also get the result in the R console. Now, if you're not using R Studio, you would just be using R within a console, which is this. And this basically works like a bash scripting shell. But the nice thing about RStudio is that it gives you both the console as well as this interface for writing R Markdown and testing out your code block by block, bit by bit. So returning to the calculations, you might say 5-trip day to Seattle costs this much. Okay, 1215. But the important thing about R is that it's an object-oriented programming language. So what you want to normally do in R is store the results of these kinds of calculations in R objects. Now, the commands are either expressions or assignments, and an expression, when written as a command, is evaluated and printed unless you specifically don't want it to be printed, and a value is lost. So that's what I just did here, where I just had this mathematical formula, printed out the result in the console, but that result is essentially lost unless I put it in an R object, which is what I do here. And I hope that this will give you a quick sense of why R is powerful and how it generally works. Here's the object. This is a vector, which is our trip to Seattle. And it's the object is assigned, which is a way of storing this information, using this arrow symbol, which is just the less than sign followed by a hyphen. You can also use an equal sign, though I find in R, more people use this arrow sign. So now what we've done, if we hit Command Enter, is that we've done the same mathematical calculation that I just did, but I've stored it in a vector called c.trip.v. And say I'm comparing this to another trip to Paris. I run that calculation. And then here what I've done is I've set up a Boolean expression that's Seattle trip is less than the Paris trip. And if I run that code, it says false, which is to say the Seattle trip is not less than the Paris trip. So I just answered the question. We should go to Paris, right? But we can also add those two objects together, and we can learn that a Seattle trip and a Paris trip costs $1,955. And if you want to consider other options, you could create a new one like a trip to New York City with various values attached to flights, hotels, etc. And we can even combine all of the objects that I've just shown you by running these code blocks that give us these options. Now, I hope that you can see why this is powerful. Instead of having to redo these calculations on your calculator, you can store the values in objects and refer to those values over and over again by invoking those objects. And that's simply by creating a new object and using this arrow identifier or operator that assigns the value. Now, what I'm doing here is a pretty common operation in R too, which is I'm creating a new object that combines all the other objects. So if I want to know the data of all of the trips that I just created, I'd create a new object called trips and invoke, and using the C function, which is basically the combine function, I'm combining the data of the three objects that I just created. And I plot it. And what we see below very quickly is how much each combined trip costs. So very quickly, you can figure out what's more affordable and what's less affordable. Now, I should say, I've actually done this myself while planning holidays, so I can personally vouch for its effectiveness. But most of the time when you're working in R, you'll probably want to read text files or read data. The most important kind of data format in R to start with is the vector. And this is essentially a word for list. And there are different kinds of vectors and different kinds of lists, as we'll see later. But it's a single variable that consists of an ordered collection of numbers or words or both. And using the C command, which I already showed you, you can very quickly create vectors. So here we've got a vector of 5 words, and you can check the vectorization. Okay, so now I've created a list with 5 words in it. But you can also use the syntax of the bracket to identify a specific value. So say I want to find the 4th word in my vector. I put 4 in an angle in a square bracket, and there you get the result of the 4th word. Now, if some of this is already being, if some of this is already confusing to you, you should do your best to look up various help pages. The easiest one is the question mark preceded by the function. And here on the right-hand pane in RStudio, the help page immediately pops up. And you can see that I was not inaccurate by saying that C is a combined function. And so it describes it for you, and it shows you the usage. And it shows you the possible arguments, and the arguments are essentially what go inside of the function after parentheses or commas, and some details and some examples. Sometimes these are hard to read because they're written by and for engineers, but oftentimes I have found them useful. And sometimes you just have to go to R bloggers, which is a good help site, or CRAN's website, or even Stack Overflow if you want a more plain spoken way of demonstrating some of these functions. Thankfully, C is a fairly easy function to understand. You can also use the example function to get some written examples of that particular function. And here I have echo false because if I were to put true, it would list for you all of the examples, and that would take up half of the notebook page. And that would be kind of annoying. The C function you'll see quite a lot in R. It's probably used less often to create vectors of text mining, related to text mining, that is, but it is often used just for putting together strings for example, for visualizations. You'll see the C function often used to put headings on various graphical results and things like that. So it's a good one to know. But the C function really won't help most of us who are interested in text analysis at first. So what you need to know to get started on that is that there are two main operations for loading text. The first one is scan, and the other one is read table. Most of you will use scan if you are loading TXT plain text files. Read table can be really great if you have CSV files. So if you have your data already loaded in a CSV file, you should use read table. And R, by the way, is very good at handling well-structured CSV because it can be very easily transformed into data frames for analysis. So to get started on our first quick text analysis, I want you to download a TXT file of Charles Dickens's Great Expectations. And what we're going to do here is create a vector called Dickens.v. I put .v in there because I just want to remind myself that this is a vector. There are other ways of knowing what kind of object it is, but it's just a habit that I picked up from Matthew Jockers. So Dickens.v is being assigned a scan function, as we just said, for loading text files, and followed by that, in parentheses, we have the text file that you just downloaded. The what option is really important when you have complicated files, particularly files that might have non-character entities. So if you want to only scan for characters, you should use this. The sep equals \n is a way of saying, is just a standard way of scanning text files that's very helpful. Sometimes you'll want the encoding option in there because some text files might not have standard encoding and you'll get errors during your text analysis. So just to be safe, I often add the UTF-8 encoding option so that I don't have any weird errors with special encoding. So after I hit Command Enter on this, I've created a vector. It says that it's read 3,913 items. If you want to check, you can just invoke the Dickens vector, and look, the entire novel loads up before your very eyes. Which was probably a bad idea because now the whole novel is showing all the way down. This is a good example of being careful before you check what your vector is. If you create a vector of a directory of 25 novels, I would not invoke that vector in RStudio because you will get a huge list. So thankfully, there's a max print issue that didn't print the entire thing. So now that you've loaded the text and now that R was able to read the text, you can run some quick statistical operations. One of the easier statistical functions is length. So tell me how long it is, right? In this case, we're finding the number of lines in the book. You'll recall that I vectorized Dickens, and what that essentially did was it created a numbered list of each line in the book. So that's why we have 3,913 lines, not 3,913 words or chapters or whatever. It's a good reminder that when you're vectorizing, you should bear in mind what kind of data you're loading and how long it is to test to see if you're loading things the way you want to load them, if that makes sense. Next, what we do is we want to lowercase all the words in the vector. And that is we simply invoke the toLower function. And I hope you're starting to notice a pattern where almost every step that we engage in R, we're assigning to a variable a function. And the function toLower is applied to the Dickens vector that we created. And I like to run each line by line because you get to see your progress here in the console as well as below here if the results can show. Next, what we're going to do, and this is sort of bringing things back to where Gabby was, is we're going to create a new variable called Dickens Words. Now you might be asking, why are we doing Dickens Words? I thought we just loaded the whole text. Well, we did, but if you go back to the length variable, you'll notice that what the vector is saying is this is a list with 3,913 items. But if you want to have a list of every single word, clearly there are more than 3,913 words in the text. So what we need to do is we need to split the vector into individual words. But as Gabby was also showing in the regex exercise, if you don't have specific instructions in your code for finding things, it might find things like blank spaces, and it might find things like punctuation. It might find all kinds of things. So one option that is available to you in R, and you'll see this a lot in R, is to use a regular expression to make your results more accurate. So here we have a variable, Dickens.words. We invoke the str split, which is string split function, to the previous object that we created, Dickens.lower.v. So once we tell string split, iterate over this vector, and then we put a comma and a value here. I hope you'll realize, having listened to Gabby, that this is a regular expression. This is a regular expression that says split the strings of the text file by finding nod word spaces, which is basically a way of saying when you're creating the list, start a new list item whenever there's a white space. And one way that you can check on how your data is classified is to use the class function. So what we did above, we created the object, Dickens Words. We want to see what kind of class that is. And if you look on the console, it says it's a list. That's good. Now, let's say we want to figure out the length of this new item that we just created. We can use length. This is one thing I just want to pause and point out, which is I started typing, and I've got a drop-down menu in RStudio of my objects. So that reduces a lot of error because you tend not to have as many typos. So let's move on to the next step. We want to take that word list that identified the each word by its word boundaries, and we're going to unlist it. And now check the class designation again. And now instead of having a list, we now have characters. And that essentially gives us an object that shows us all of the individual words in the text. And here we can test that by invoking the words object and in square brackets giving a range. So instead of saying, well, let's just do this. What's the first word in the book? Chapter. Okay, that's good. You'll see that it's now lowercase, and you'll see that there are no white spaces or punctuation, so that's good. If we want to get the first 50 words of Dickens, we can use a range. So using the colon. So now we have the first 50 words. I'm sort of skipping ahead a little bit, but you'll notice there's the problem. There's some blank spaces still. How can we deal with this blank spaces issue? We need to do a little cleanup. So we'll create a new object, yet again. We're going to be creating lots of objects called not blanks. And what this does is it uses a function called which is basically a way of saying, find me something in the text. And what we're finding in this word vector is something that is not a blank. That's what the exclamation mark refers to, not equal to a blank, okay? So we use that. And then what we do is we create a new version of the Dickens word.v object by stripping out the not blanks, or stripping out the blanks by just focusing on the not blanks, if that makes sense. So we'll go back. I had 1 through 10. You can do 1 through 50. And there you go. No more blank spaces, no more blank words, just words. So that's good. So you can see how the regular expression got us about halfway there, but it still required some extra cleanup. And you'll see more of this in a moment. Now, we might want to also examine a specific word. We noticed up here in our first 50 words that father was the 4th word result. And if you've read Great Expectations, you might be thinking to yourself, well, father, that's probably an interesting word. Let's have a look at that word. So using the length function yet again, we can examine the length of this particular word vector by invoking that function which again, which says find me in the vector this particular word. Now in R, whenever you're trying to find some equivalence, you use 2 equal signs. And here you can see that the equal signs refers to father. And when we hit that, we get 69 instances of the word father. That's a fairly high amount of that word, you might think. How does that compare to the total amount of words in the book? Again, using the length function, and then within the length function, invoking the unique function, we can see how many unique words are in the Dickens words vector. So that's 10,760 unique words. Now you can bring back your mathematical operations by dividing the amount of words in the whole book to calculate vocabulary density ratios. I was somewhat afraid to bring up vocabulary density because it's somewhat of a controversial topic in linguistics about whether it's actually meaningful to calculate vocabulary density, type token ratios, or hapax legomena, etc. But sometimes it's revealing, and sometimes it just reveals the length of the text. But let's do it anyway because it might interest you. So we're going to create a new object, which is a unique words object. And again, we'll see the length function and the unique function that are nested within each other to find unique words in the Dickens vector. And another object for the total amount of words, so just the length of the entire vector. And then using a simple mathematical formula called division, we can take the unique words and divide it by the total words, and there you go. We've just gotten the number for the type token ratio of the book, which is, you know, roughly 5.7%. Not as high as Melville, I'll say, and I say that as a Melville person, so naturally I'm proud that Melville had a high type token ratio. But of course, he wrote a longer book. Anyway, the other important data structures that you should know about are tables and data frames. They're pretty useful for sophisticated analyses because you essentially turn the data into labeled tables with columnar data. So it basically is like the notion of the spreadsheet, that you have individual labels for each type of data that you're interested in. I'm going to stop sharing for a moment. Does anybody have any questions before I move on? Am I making good sense so far? Yes, no, maybe.
Yes, well, there doesn't seem to be any questions in the chat now. Does
Okay.
anyone else have a question?
I just wanted to make sure, because I'm staring at my R notebook and not at the presentation. So I will move on. Okay. So when we get into more advanced kinds of programming tasks, we're often using things like stochastic simulation. And what this basically means is that we create programs which are repetitive operations and pattern recognitions. And these are two of the more important reasons why we use programming languages, as you're seeing on the screen. One of the most important aspects of programming is the for loop. And this is something that you'll see in every programming language because it's so important. In R, the way the syntax works is simply starting with the word for, and you create a name for the for loop, and you identify a vector that it will iterate over, and then following that, you have the curly brackets. And within those curly brackets, you enter a series of commands, not unlike what you just saw above, where we were processing individual lines of code over Dickens's text. But with a for loop, you can essentially program it so that there are instructions for handling various operations. Here I've got an example of the Fibonacci sequence. This just shows you how you can create a for loop that can just generate quickly the first 20 Fibonacci numbers. Those of you who are fans of the band Tool might know that one of their songs, Lateralis, was based on a study of the Fibonacci sequence. Well, if they had only had R, they could have been even more precise in studying Fibonacci numbers and incorporating them in the music. But who knows, that may have made them even crazier. Are we being taped? I suppose we are. So anyway, the way that this generally works is that we've created a vector called Fibonacci, and we're just defining this as a numeric object, so numbers, with 20 numbers. And what we do here then in the next step is to take the first numeric object in Fibonacci, and we've got the first and second elements with the value of 1. So if you know the Fibonacci sequence, the first 2 numbers are 1, and the third is gained by adding the first 2, and so on, as I say in these instructions. Now here's the for loop. It's a fairly simple for loop. It says for parens I in 3 through 20 in Fibonacci. And there's a formula, and I explain in the comments here exactly how that works. And what you get is a list of the first 20 Fibonacci numbers. So there you go. There's the first, there's the second. You add them together, you get 2, you get 2 plus 1, you get 3, and so on. Cool, huh? So you can automate the Fibonacci sequence just by creating a fairly simple for loop here. Now, there are other kinds of elements of what we call stochastic simulation, really important ones, the conditional. There are 2 kinds of conditionals that take the form of if statements. And here I've given you the syntax of conditional statements. These are fairly complicated and particularly probably too complicated to get into for intro to R, but I want you to see this and to digest it as best as you can, because soon you'll see how an if conditional is embedded within a for loop, and how that's a very important aspect of programming that you see in Python, in XSLT, in all kinds of programming languages where you need to set conditions for processing certain types of data. So what I want to do now is show you an example of a fairly complicated for loop that's taken from Matthew Jockers's book on text analysis in R. It's a very good book. It's a very good introductory book. In fact, I started with it a few years ago when I started learning R. And he gives you a fairly basic yet complicated and useful way of taking a novel text and stripping out the metadata and focusing on the text itself and generating a table, or a list that is, of word frequency, relative word frequencies throughout the entire text. I hope what you'll notice here is that it has various elements of things that we have been talking about, not just including assigning variables or assigning values to vectors. We've got the scan function, which of course loads up the Great Expectations text, as we already saw. What we're doing here is using the which function again, which says find me the string that starts chapter I. So here again, we're just finding a literal equals operation of find me this string in the text. And that's the start of the text. And then we've got the end of the text, which of course ends with the end. So we run these two, and now we've got 2 objects that indicate the start and the end of the novel, which is important if you're working with a text file that has a bunch of metadata, or if you're working with Project Gutenberg files, for example, that have a bunch of stuff in between the text that you don't really need. And we've created a new object called novel.lines.v, which goes through the text vector and combines the start and the end. And next what happens is a regular expression, except here we've got a more explicit version of a regular expression, which is grep. And grep, of course, is the function which is a regular expression match. So what we're doing is we've got a chapter positions vector that matches any word or digit, well, character or digit, that is, that follows the word chapter. So that's a fairly simple regular expression, but very powerful, because it's what it's essentially doing is finding it's giving you instructions for finding the beginning of each chapter by using this regular expression. Find me the word chapter followed by a digit or a character within the novel lines vector. This might seem kind of tedious, but it's important. When you're doing for loops, you often want to create a container for the for loop. Otherwise, the stuff that you find in the for loop won't go anywhere. So we're creating two list items that will be the containers for Jockers's big fancy for loop. Here again, you'll notice another regular expression, which is exactly the line that we've used before earlier in the notebook, where we're using the string split function and finding each word in each chapter and separating each word by its word boundary. So we're seeing some repetition here. Now, if we run this for loop, we've now created a list of relative frequencies of each word in the novel. And I hope you saw how quick that was, just a few seconds, even less than a few seconds. Now let's go back to that father example that, that we used earlier. And let's be a little more mathematically precise about the father example. So we create an object, say, of the word father, father.freaks. And we use a new function called lapply, which finds within the list that we created above here, the container, it finds the word father. Easy enough, right? So now we've got a new object which gives me all the relative frequencies of the word father in each chapter. And if you run the vector itself, you'll see that in chapter 1, the word father occurs 27% compared to the rest of the text. Chapter 2, it doesn't appear at all. Same for 3, 4, 5, 6, etc. And what you can do is you can simply go through each chapter and have a look at where the word is appearing and what its relative frequency is compared to the total amount of words, which might be very interesting if you're trying to trace the fluctuation of this word throughout the text and what that might say about the style of this text. And particularly if you're reading the novel in an ordinary linear way, how that coalesces with your reading, how the computational results coalesce with your reading. There are other versions of the which function which can immediately identify for you things like the highest example of whatever your object is, so, or the max example that is. So if I want to find the chapter that has the highest frequency instances of the word father, it's in chapter 22, and in the minimum, it's in 53, chapter 53. So you can see, I hope, how quickly you can find really interesting information and sort of mathematically pass it through R and learn some things that might have taken you many hours of labor to try and figure out on your own by, say, highlighting each instance of the word father and then plotting out where it occurs and where it occurs the most. This is why we use R, because we can figure out these things very quickly computationally, and it's accurate insofar as the text that we're loading up is accurate. With the rest of our time, I want to go through the tidytext library and show you some examples of some other things that you can do in R using this very effective library to essentially engage in some distant reading. And I've just chosen a classical author because of your seminar. And I should say that I'm not a classicist. I'm an Americanist, I guess, or 19th century person. So I don't know what good texts might be appropriate, but I just picked some at random. So forgive me if this is a bad example, but you'll have your own opportunity to pick some examples that you like. I've given the link to the Tidy Text Mining book, which is an excellent book, highly recommended. And most of the code that we're using is modified from their work, Julia Silge and David Robinson, that is. One thing I want to do really quickly is just to remind you some basic stuff, like, are you in the right working directory? If you downloaded the text file from Great Expectations, for example, that download went somewhere, and you might be having some problems at this point because, say, it went in your downloads folder, but your R notebook is on your desktop. So you just want to make sure you know where you are in your file system when you're doing these kinds of programming tasks. And generally, you want to be working with files that are all in the same directory or subdirectory within a directory to make sure that you're calling upon the right things. Now, if we go down to the console here, we can just use what looks like a bash script to find out where in my filing system I happen to be. And this is just using the R function getwd parens, which is get working directory. And you notice that that explanation is very helpful. So it's telling me that I am in my Dropbox. And that's fine, even though I tell you you should be in your desktop. The files that I'm using for this demo are in my Dropbox. So it's good that I'm in my Dropbox. But say I wanted to change it to my desktop, I would then use the function setwd. And then within that, I would indicate my desktop. And then you could hit enter, and that would get you to your desktop, such as you have it here. And by the way, this tilde basically says go back to the root of my filing system and move from that to the desktop, which is usually the next step. So that's another good practice. So once you're within the filing system, what you need to do is load some libraries, which is first and foremost the tidy text library, but also dplyr, which is a really important R library that a lot of people use, tidy R library, the Gutenberger library, which will be helpful in a second, as you'll see. I've already preloaded these libraries. If some of you get any error messages on these libraries, what you'll need to do is click on packages over here and click on install. And say you're not getting the dplyr, you'll want to find that on your packages, and thankfully there's a drop-down menu that shows you these things, and you just click install. And once you have the package installed, you can then just do Command Enter on all of these libraries.
For the record, for me, that was about 2/3 of them.
Yeah, sometimes you need to download a lot of them. Sometimes there's just one or two, so it depends. Because I've worked so much in R, I probably didn't need to download any of them. So yeah, once you have installed all the packages you need. Oh, and by the way, not to jump ahead too far, but when Maciej does Stylo, Stylo is one of those packages that you'll need to install. So you may as well right now just go to install and find Stylo and download that, so that when we work on Stylo, you'll be ready for that. Right. So what I want to show you is very quickly, because we're running out of time, how you can use the tidy text package and the Gutenberger package to achieve some pretty quick and amazing text analysis results. Here I just have the Gutenberg authors function from the Gutenberger package, which shows you your way in to engaging with Project Gutenberg's text corpus. And this just shows you the kind of syntax that you'll need to be aware of if you're examining authors, for example. So you usually it's last name, comma, first name, but there's also authors like the United States, which frightens me a little, I must say. But of course, we want to load files, and that's why we're here. Instead of using scan and downloading a local copy like we did before, we're going to use the Gutenberg_works function, which is a really quick and handy way of finding authors. So remember the string detect function. We're just looking within that for an author called Livy, and then separating this by title. And this is just a way of referring to a variable. So by doing that, we see 5 results for books by the Roman historian Livy. And the reason why I showed you this is because most of the time when I have done Gutenberger work, I find that you sometimes get some duplication of titles. So it's important to look at the titles and make sure that you're not double downloading anything. So in this case, you want to ignore the first result because it gives you books 1 through 3, and it's probably a different translation and so on. And as I say here in the notebook, trust no one. That is the first rule of scholarship. And of course, in computing, you should always trust your data because data tends to be messy, and the computer will only give you results as good as your data and your instructions for that matter. So what we do here is we, to get going on Livy, we create an object which I've just called IDs, which is probably a bad name for the object. I apologize. And what we're doing is doing the Gutenberg works download function, except we're identifying it not by title, but by the Gutenberg ID, which is important because the Gutenberg IDs are listed here 1 through 5, and we want to skip the first one. So we have a range here of the 2nd through the 5th result that we want to download. So we do that, and then we create a new object called Livy, which is taking all of the books that are contained within the IDs object, and we download them. And then, behold the magic of the tidytext package. We translate the Livy object into a tidytext tibble, which is basically a data a vector, that is. I've got some instructions here about learning more about some of these Gutenberger functions, and also some explanation about the $sign and the pipe, which is this. That it's just a connector that's used in some packages in R for writing basically more readable code. So instead of embedding these arguments within each other with multiple parentheses, you connect them with a pipe, which is this symbol. Right. So now that we've downloaded all of Livy, you can get some fairly quick statistical results just by doing a summary function. It tells you various things that might be of interest. Sometimes they're not. But the most important thing that we're going to do here is we need to take that Livy vector and we need to tidy it up. And what we're essentially doing with the tidytext package is tokenizing. And tokenizing is a fancy way of saying taking each textual bit of textual meaning and putting it in an individual list with various labels attached to it. So what we're doing here is we're tokenizing the various words in these various files, unnesting them just like we unnested the words previously with Dickens, and we're outputting words, and those words are tokenized as words rather than as, say, roots or characters, which is another way of tokenizing. But here we're tokenizing as words. So now let's take the tidy Livy results, and we can plot them pretty quickly using the tidytext package. And you can see that the first word that appears is the and of, which is a really interesting result because it basically tells you that this is a narrative about things. It's not as action driven as, say, poetry would be. And these are function words, and for some linguists, function words are extremely important. Whereas for some others who are interested in unique words, for example, in terms of style, which we'll hear more about in a couple weeks, function words are less important. But if you're interested in function words, you can get those very quickly by plotting with ggplots function the results in the tidy Livy data frame. You can very easily strip out the function words by using the stop words function within data. And there's a function that tidytext uses quite a lot called anti-join, which is essentially a way of saying take away from the data set X. So what we're doing now is transforming tidy Livy into a list of words that does not have stop words. When you do sentiment analysis, for example, you'll notice that tidytext uses the inner join function to do sentiment analysis. And that's a way of marrying two data types, bringing them together. But in this case, you can use anti-join to take things out. And then we can plot that just like we did before. And now we've got a bar graph, that is, of the 600, well, the most frequent words used more than 600 times in Livy. Wartime and enemy. I wonder what Livy was talking about. Yeah, so pretty interesting results. I don't know that much about Livy, to be honest, so I think I know more about him now just by looking at some of these results. Is that cheating? Maybe, maybe not, but it's computationally accurate, and that's what's most interesting to me. Oh, right. So one thing you can do in RStudio that's very helpful is you can take some of these complex visualizations and click on this arrow button here and maximize the view so you can read your results a little better. This is actually a way in which the RStudio IDE works better than publishing this in HTML. In HTML, the results are sometimes hard to read, but here you can blow these things up. So one thing you might also want to do is to transform what we've just done into something that you can download onto your machine and use for word searching purposes. So just performing simple word counts of the tidy text tibble, the data frame, that is, and sorting it by frequency. And then here we're just using a simple R function, write_CSV, which is just a way of outputting the results that we've generated into a CSV file. So we invoke write_CSV, and then we invoke the object Livy words, which is here to here, and then we can write out the file name .csv, and low, you can open up the CSV file on your machine, and there you go. All the Livy words. The first word war occurs 2,520 times. You can, of course, do Control F and see if the word father shows up. Oh, look, there it is. 118th most popular word, used 356 times, since we're on that father theme. So this can be a very handy way of taking this tidy text information and outputting it into a simple spreadsheet. I've left here in the comments a way that you can also create a new CSV of the tidy text table and what it looks like before you have changed it here into just a simple word count. If you were to create a CSV from the tidy Livy, you would also get which book, for example, each word occurs. I've added here that a lot of what we're doing now can be done in Voyant Tools, but and if you don't know Voyant Tools, it's a very impressive web-based and free tool for doing text analysis. But I hope you'll notice that when we use R, we can manipulate the results much easier, and we have a lot more flexibility with how we want to restructure data, how we want to investigate it, and how we want to visualize it. So most of what I've just shown you, you can't really do in R. And certainly what's in the rest of this notebook and in the session a couple of weeks from now, these are just things you can't do in a web-based program that's sort of pre-built for you. We're giving ourselves a lot more agency over how we want to manipulate data and find out more about it. What I've done here is shown you some code blocks for, similar to what Jockers did, splitting up each tidy text data frame by book. So instead of by chapter, we're doing by book because we're simply grouping each item by its Gutenberg ID rather than by a chapter. But of course, you could use a regular expression within this to identify, instead of a Gutenberg ID, say Gutenberg ID followed by a regular expression. And it looks like we are nearly out of time. So I want to pause and see if we have any questions.
So we are more than nearly out of time. We were out of time 26 minutes ago, but the thing I would like to think about at this point, because I mean, you've got more in the sheets that people can look at in their own time, and that my students, at least, we will look at with them next week. But one thing I wonder if we could think about a bit is a couple of so there are some exercises there in terms of working through this, but I wonder if we might suggest to people who are still at this point not having worked through it themselves yet, might want a couple of slightly more basic exercises to start nearer the top. And I was wondering if you know, the exercise on, you know, loading in a text and just doing the very basic things that you did with Dickens. So before we got to tidy text, just so they can practice a little bit of regular expressions, they can practice a couple of other things, so maybe cleaning up the text. So I wonder if we might want to suggest that people you know, try out a few things just by changing the code that is in this tape, in this notebook, right? Not necessarily having to go off and program all on their own.
Right.
Do you have any more concrete suggestion than that we could look at just briefly, or should we just let people play?
What I can do is let me think. I agree with you that it would be good to have another basic example of loading and parsing and changing some text. What I can do is I can add a code block to the notebook and go from there, because I'm failing to think of anything off the top of my head. I'm sorry.
Sure. No, that's fine. So yeah, just some of the basic stuff on working with the paragraph, the text file and so forth before we get to tidy text and so forth.
Okay.
Suggestion to the students to try this out. To play with changing the various parameters in the existing code block, so they can just to check that they understand it.
Right.
yeah, as I say, for my students, we will talk about it next week, and we may, and presumably other people who are using Sunoi courses will have a chance to go through it with them at some point as well. So basically, just to reassure people that if they didn't follow every single thing that went on in this session, go as far as you did understand and start practicing that, and we'll take it from there. Because it's not if you did understand everything and you worked through the entire notebook, including the bits that Christopher didn't get to, then that's brilliant. But you're probably way above average for what we would expect a first-time programmer to have gone through all this.
Yeah, I think I wanted to show what was possible beyond just word searching, but also, it's important for me to emphasize, I think, that you don't necessarily have to get all of it. You just need to know how to modify code that people have already written. So a lot of the code that I'm showing you in this notebook was not written from scratch by me. It was modified from other people's code. So I think that's an important skill to learn, in addition to doing some of these basic things that we should also learn at first.
Yeah. Thank you very much, both of you. And I think this was clear presentation introduction, and I really got interested. And still reminding the people who are watching that the notebook that Christopher was using is really downloadable there in the Sunoikisis GitHub page. And also the readings provided there, the extra readings, where some of them I'm not familiar with, or so what I was doing was following some of those things. So it seemed like a very doable thing to start to get to know this. Anissa was asking in the chat that what would it be to practice with an annotated text, but perhaps that's something that after the second session of using we are getting to the annotated text.
Yeah, I think one of the things that Robert Gorman wants to show in 2 weeks is taking the XML from tree-banked text, processing that with R to, as you put it, get rid of the XML as quickly as possible and get out chunks of data, and then do stuff with that. So that's one of the things we will be looking at.
Right.
Okay, so I think it's time to end this session, and thank you again, both of you. And as said, we will have more of R in 2 weeks' time. And next week, there is an intervening session about digital paleography. So please welcome back then. And good night.
Thanks for having me.
Cheers.